NASA's upcoming Artemis mission will mark a significant milestone in U.S. spaceflight history when it lifts off in late 2024. Not only will it be the first time that American astronauts have traveled further than low Earth orbit since the 1970s, and not only will it be the first opportunity for a female astronaut to step foot on the moon. The Artemis mission will perform crucial groundwork needed for humanity to further explore and potentially colonize our nearest celestial neighbor, as well as eventually serve as a jumping-off point in our quest to reach Mars. However, the challenges involved in actually residing on the moon, or Mars, are significantly harder than the so-called flags and footprints missions wherein astronauts set down on the surface, take a few selfies, collect a few samples, and then return home. Luckily, NASA has a plan. The idea of landing and staying on the moon was long considered folly by the spaceflight community, a notion based on the overwhelming lack of moisture found in regolith samples collected during the Apollo era. That changed in the mid-1990s when NASA's Lunar Prospector mission first found telltale evidence of hydrogen atoms located at the moon's poles, suggesting the potential presence of water ice. Subsequent surveys of the moon uncovered additional evidence of frozen water on, or at least near, the lunar surface, and confirmed it last October when the SOFIA mission detected ice located on the sunny side of the moon, not just in the deep dark recesses of shaded craters. As Rob Mueller, senior technologist in advanced project development at NASA, said during a South by Southwest 2021 panel,
"There's enough water on the moon to launch the space shuttle, a vehicle like the space shuttle, every day for 2,000 years. So there's a lot of water on the moon. The trick is we have to find it, access it, and mine it, and then economically use it."
Water is an extremely valuable resource for space travelers as it serves to both hydrate the astronauts themselves and power the rockets on which they ride. But extracting water from the moon is harder than it sounds. A significant amount of it is trapped in permanently shadowed regions where the ambient temperature can drop to as low as 40 degrees Kelvin. That's colder than liquid nitrogen. It's so cold, in fact, that exposing metal to those sorts of temperatures can weaken it to glass-like fragility. Not exactly the sort of material properties you want when digging through rock. The moon in general sees some wild thermal swings between its bright and dark sides. Temperatures can approach 125 degrees Celsius in the sun and drop to as low as negative 175 degrees Celsius in the shade. But regardless of the difficulties in extracting it, water remains so valuable to space travel, some researchers fear that its discovery could lead to a resource and land grab the likes of which we haven't seen since the Yukon Gold Rush. Would-be water miners will also have to contend with the moon's thick layer of razor-sharp electrostatic dust. Created from eons of regular micrometeorite impacts across its surface, moon dust carries a powerful static electric charge which causes it to readily cling to spacesuits and rovers alike. If tracked back into the astronaut's habitat, the stuff can and will clog filtration systems, short out sensitive electronics, jam zippers, and freeze mechanical joints. And that's assuming you don't get conked out by a falling micrometeorite while roaming the surface. NASA has developed an anti-static coating to counter the dust's electrical attraction, but its effectiveness at scale has not yet been tested.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
When America made its initial push into space, we did so alone, and our efforts kinda kicked off the Cold War. This time around, however, the US is partnering with both the international community and private enterprise. Just last month, NASA announced a $331.8 million deal with SpaceX for the aerospace firm to deliver two portions of the Lunar Gateway orbital platform to the moon, where it will serve as a base of operations for future missions, enabling astronauts to simply shuttle back and forth to the surface rather than travel directly from Earth to the moon.
So Apollo was arguably the pinnacle of human achievement ever, arguably. It was also very expensive, and it required a driving force, which was the Cold War, and really a survival instinct is what drove us to go to the moon. It was part of the Cold War, and it was very expensive. This time we're going to do it differently. We're going to have international partnerships. We're going to have commercial partnerships. And this will let us do it for a reasonable cost with arguably a return on investment, a large return on investment. But we can't do it as NASA alone. NASA is a government agency. The role of the government is to facilitate industry. And so that's what we're doing. We're setting up the framework, the infrastructure, and all the processes, the legal framework, communications, launch sites. This is all necessary. And then private industry can come in and do what they know how to do, which is make some money, create an economically efficient system.
Partnering with other nations will help offset the massive upfront costs of such a mission, but that can lead to potential conflicts as to which member nation will get access and rights to which resources. Currently, such matters are governed by the United Nations Outer Space Treaty of 1967. However, its language is not entirely clear, leaving the rules open to different readings.
The U.S. government, they have interpreted the Outer Space Treaty in a different light than some people have. The U.S. interpretation is that we will not claim the land or claim sovereignty, but we do have the right to use resources, and commercial industry has the right to use the resources. And this is law in the United States, so any entity that launches from the United States does have the right to use the resources on the moon, but you cannot claim the land. And that's really the essence of it.
What's more, the Outer Space Treaty lacks specific enforcement mechanisms and has yet to be ratified by any signatory nation, making its rules more of suggestions. The Artemis Accords, which were created specifically for this upcoming multinational mission, similarly are more guidelines rather than directives. Living on Mars for any appreciable amount of time will force astronauts to overcome many of the same challenges that they'd face on the Moon. Large temperature swings, pervasive dust, this time windborne, and micrometeorite strikes. Except this time they'll be dealing with these issues at the opposite end of a 6-month-long spaceflight from Earth. Self-reliance won't just be a virtue for tomorrow's Mars colonists, it'll be a requirement. These explorers will also have to contend with both solar and galactic radiation, both of which are quite deadly. To escape that radiation, lunar residents could one day live under inflatable domes covered in 3D printed shells made from the Moon's own soil. Martian explorers, on the other hand, might need to pick their settlement site more carefully, relying on natural topographical features like valleys and cliffsides to help minimize exposure to such deadly rays. But should we manage to surmount these challenges, the rewards will be substantial. Humanity has already shown that it's capable of inhabiting some of the most inhospitable areas of the Earth, such as Concordia's station in Antarctica. With continued diligence, research, and international cooperation, the stars themselves could soon be within our reach.